Lesson 8.3, graphing reciprocals of linear functions. So if you recall, a reciprocal is when we flip a fraction. So for any whole number, the reciprocal of that whole number is 1 over it, because remember that it's actually written over 1. We never write it like that because there's really no need. Anything divided by 1 is itself. The reciprocal of that reciprocal is then our original. So it's flipping back and forth of fractions. When we do this for a function, we are literally going to take the output, okay, and remember that f of x on the whole is the output, which we frequently represent as y, okay? So we're taking the output and we're going 1 divided by our output. And the only thing we have to watch out for is that as a denominator, we can't have our function being 0. So we're going to work through this first one together just to kind of wrap our heads around it. So we're going to graph f of x and its reciprocal, assuming that f of x is equal to x. Or we can think of it as y equals x, which is what we see in our table here. So if we choose some values for x, like -3, 2, -1, 0, 1, 2, 3. Then when we plug it in, well, y is equal to x, so it's the same thing. So that makes this column really easy to fill in as well. Now, when we go to fill in the reciprocal, so again, this is f of x. This is our reciprocal of f of x. When we take the reciprocal of it, what we're doing is x stays the same, okay? Unchanged. It's just our output that's changing. We're doing 1 divided by it now. So in this case, 1 over 3 is -1/3. It's going to be -1/2. -1. 1 divided by 0 is not possible. So there is no value. And you would get an error if we punch that into our calculator. 1 divided by 1, still 1. 1/2, 1/3. Yeah, so if we go to graph this, first we'll graph f of x. So putting our coordinates on here. I'm going to go up by 2, so 1, 3. Create your y and x labels, or rather I'm going up and down by half each grid line. And I'm going to plot my points. So for f of x, which I'm going to color red, it's going to be -3, -3, -2, -2, -1, -1. Oops. The negatives on those. Don't do that. 0 and 0, 1 and 1, 2 and 2, 3 and 3. And we can connect that all with a line that goes across our entire grid. Apologies for my shaky hand. Okay. Alternately, if we're going to graph our inverse, well, we've got -3 and -1/3, which would be about here. So what I'm going to do with f of x. Then I've got -1/2, which is here. Then I've got -1. And I have no value here, and over here I'm going to go +1/2, 1/3. Okay, so what ends up happening here is we need to consider a couple things. When we divide by 0, at no point is this allowed. This creates what we call an asymptote. Okay, And it is a value where x is, it's basically our non-permissible values is what it is. Okay, and where x does not exist. So the symbol for existing in math is a backwards E like this, and we can put a line through it. It doesn't exist. Okay, so what happens is we do a dotted line to represent that asymptote, and then we name that asymptote just like we would identify our non-permissible values. So x equals 0 is my asymptote. It's now you'll notice my non-permissible value is that x can't equal 0. The name of that line though is that x is 0 because that's where my asymptote exists. So that's one thing to watch out for. It's equal to when it's technically not equal to. It's a little weird. The rest of my graph, well, I can connect these 3 points and kind of see what's going on. What actually ends up happening is we get a horizontal asymptote as well, because y will also never be 0, because it's impossible to turn 1 over something into 0. Okay, because if we divide by 0, then we're hitting our horizontal asymptote. So we've also got an asymptote at y equals 0. So how does my graph behave approaching an asymptote? Well, it kind of starts curving and you'll see it kind of flattens out, and it looks like it's going to be flattening forever. It's never going to get to the point where y equals 0, but it's going to get really, really close. So when you go to draw these, just make sure that you don't curve away from it. Don't do that, okay? Because that kind of defeats the purpose of the asymptote. The behavior of a graph typically around an asymptote is that it will get really, really close without crossing. Now, you're going to get to a point in your math career, if you pursue math further, where you will be allowed to cross an asymptote. But we are not in that place. We are not in that time. So just be aware that it does happen eventually. But for us, absolutely not. No crossing of asymptotes. Just approaching really closely and following along. Now this behavior between -1 and 0 actually follows the same rule. Now we can see that we have a defined point here that we haven't included in our table. But if I did add it, it would have originally been -0.5 and a -0.5. Extending my table from up here. When I take the reciprocal of a fraction, what I do is I flip it just like I do with all these numbers. And so what that ends up being is the negative sign still sticks around because a positive in my numerator divided by a negative in my denominator is still negative. Okay, so that doesn't change, but it's like multiplying by the reciprocal, and so it ends up actually being -2. So I get a point here. So we get a sense of how it's going to look over on this side. Again, it's going to approach that vertical asymptote, but never quite cross it. We're going to see this similar behavior over here. I can add in that extra point that we've just created because there is some symmetry, and get my curve like this. Okay, so again, we've got a new word. Asymptote means a place where that value cannot exist on my graph. Okay, it's typically associated with my non-permissible values. And when I draw a graph, my lines are going to get really close without actually crossing. I'm just going to name all the blue as my reciprocal graph. Okay, and then the arrows get really close to the asymptotes. Okay, one other thing that we're going to point out here is this point right here and this point right here. When y equals 1 or -1, its reciprocal doesn't change. Now you might remember that we had a name for these points. Maybe, possibly. When y equals plus or minus 1, that gives us our invariant points. Here. And invariant means that they don't change. They stay exactly where they were, even when we take the reciprocal. Because the reciprocal of 1 is 1. The reciprocal of -1 is -1. Okay? So just kind of reading through here, the function y equals 1 over x is a rational function. Okay, the second we have that exponent in the, or the variable in the denominator. Okay, that's what makes it a rational function. Okay, it has two distinct pieces or branches. These branches are located on either side of the vertical asymptote, defined by the non-permissive values, and the horizontal asymptote, defined by the fact that the value of 0 is not in the range of the function. Okay, so a vertical asymptote, so we're not NPVs. Horizontal asymptote describes the behavior of the graph for a very large positive and negative x values. So again, they never quite get to 0. So that's why y cannot be 0. Okay, so asymptotes are lines that the graph approaches but never touches or crosses. They are not really part of the graph, therefore they are sketched as dashed lines. Okay, so I'll start the next video with our next example, considering kind of how this moves around. What you might want to consider is where the line exists versus where those pieces on our graph exist as we move through these next examples.